Hello and welcome. My name is Bennett. I'm an application engineer here at LEAP, and I'd like to welcome you to our new series here at LEAP Australia on digital mission engineering. These YouTube videos are going to act as a companion to our new digital mission engineering blog and the video series you might have already seen on our website or our LinkedIn. Now, in these videos, I really wanted to take a bit of a behind-the-scenes look at what goes into the setup for one of these multi-domain system of systems simulations. And if the idea of digital mission engineering is something you're hearing for the first time, then I'll provide a quick overview before I jump into the Ansys STK GUI. Digital mission engineering can be defined as the use of modeling, simulation, and analysis to incorporate the operational environment and evaluate mission outcomes at every phase of the project lifecycle. It's this idea of bringing all of these components and subcomponents from a larger interconnected system into a single simulation environment that really takes digital mission engineering beyond your conventional, say, CFD or FEA approach that a lot of us are familiar with in this design process. By continuation, digital mission engineering, or DME, brings us to the idea of a design reference mission, or DRM. A DRM is a representative mission profile that sufficiently describes the intended system across both its nominal and its most stressful operating conditions. Ultimately, a DRM is the mechanism used to evaluate complex system performance and, in turn, guide development efforts. This can often be thought of through three main guises, namely how things move, how things interact, and ultimately how these things are going to be used to achieve a particular mission or goal. Now, crucially, each of these three steps needs to occur in a physics-accurate representation of real-world operating environments. If you'd like to learn more about digital mission engineering, be sure to check out our new DME blog page on our website. But for now, let us jump into Ansys System Toolkit to explore the first DRM in this series. Our first DRM is focused on radar, aviation, and communication via a LEO constellation. Our multi-domain scenario starts with an unidentified target aircraft passing over an offshore patrol boat north of Australia, and upon successful detection by radar, an intercept aircraft is launched from a nearby airstrip. Throughout its flight, the interceptor is required to maintain a communication link to a ground facility near the east coast of Australia, and this occurs via a LEO satellite constellation. In terms of analysis, we'll take a look at our radar's probability of detection, our interceptor aircraft setup, and the chain access between interceptor, constellation, and ultimately ground facility. So I'll go ahead and start at the beginning. For anyone not familiar with Ansys System Toolkit, or STK, I've got a 3D graphics window here where I can move about, look at all of my objects in time and space. I've got a structure tree on the left-hand side here where I've kind of built up my scenario object by object. And I've got a timeline view down here where I can look at different parts of my scenario and kind of navigate there quickly. We'll start at the beginning with our patrol boat, which has this 3-beam multifunction radar that we can see. And that is tasked with detecting this aircraft that passes overhead, emerges over the horizon, passes over the bow of the ship, and eventually travels on towards the north coast of Australia. Now, this patrol boat, if I go ahead and open up the properties for its multifunction radar, see those 3 beams in their defined form. So we've got our targeted beam, we've got a constant spinning beam, and we've got a fixed forward-facing beam as well. Now, if I come to, say, the pointing tab of the targeted beam, we'll see that that has an assigned target of target aircraft RCS being radar cross-section. So that's how I've defined my beam to track that aircraft if and when line of sight access is available. Now, I can also come across to the waveforms tab and I'll see that I've got 4 range-based waveforms here. They are short range, medium, long, and ultra long range, defined with the default ranges within STK. Now, I can, of course, change both the range intervals here and the waveform itself. Right now, I've got a rectangular waveform, and I could come into the component selector here and change that to any of the predefined waveforms within STK, or add my own external reference to another waveform if I have that information. So I'll go ahead and jump across to our target aircraft so we can have a look at how that's defined by comparison. So I'll go ahead and right click on that in my structure tree and zoom to that. And what we can see here is we can already see visualized the realistic radar cross-section that we've assigned to this aircraft. So that's visualized in this 3D graphic here. If I have a pan around that aircraft, we can kind of see how that lines up with the geometry of our craft. And of course, I could change out both the model for this and the corresponding RCS profile at any given point. Now, over there, we can see our patrol boat just on the horizon. And if I advance time a little bit, we'll see that this boat passes over the bow of that patrol boat. And we're going to start getting some radar results from this in a second. So to get those radar results, what I can do is I can right-click on the target aircraft RCS, the object. I can come down to the Access panel, or specifically, I can come down to the Report and Graph Manager. And then rather than searching by aircraft object type, I'm going to search by access. And there's already a few elements here, but this is effectively where I've computed access between my radar and my aircraft object. And I've got a few different options here just because I've kind of set up the scenario so that we can compare a realistic RCS profile versus a uniform profile. So if I go ahead and say select this first access, this third access here. So this top one is a uniform RCS profile. This bottom one is a realistic RCS profile. And I'll go ahead and generate a graph. And depending on the object that you've selected within STK, there's going to be a number of pre-installed styles for both tabulature data reports and also visual graphs within STK. So for example, I might want to look at something like an azimuth elevation range graph or report, or if I'm looking at, say, a communication link, I've got these link budgets. But in this case, what I actually want to do is I want to use one of my own defined graphs, the target aircraft beam probability of determination graph that I prepared earlier. And if I hit generate on this, we'll see that result generate there for us. So in the green, we can see that uniform RCS profile, as expected, nice and symmetrical as the aircraft approaches and then eventually passes over and passes away from our patrol boat. We can see these sharp dips. These are occurring each time our radar is changing from one range-based waveform to the next. And we can see that throughout this access interval, particularly once we reach the kind of medium and the short range waveforms, we're getting a pretty much 100% probability of detection for our current radar specifications. Now, by contrast, our probability of detection for our realistic RCS profile, here in black, is much shorter and much more sporadic. So we only get one really confident spike, and that is only for a brief amount of time. I can go ahead and shorten the time step of this report, regenerate that, and in a second, we'll just get this with a little bit more detail so that I can go ahead and zoom into that and see just how long our probability of access is at that higher confidence interval. So if I zoom into this, we're really only getting, what is that? A fraction of a minute there, where we're getting a confident detection over, say, 90%. And if I go ahead and zoom back out so we can view that whole graph, we'll note that the confident detection, these kind of three main spikes for a realistic RCS profile, actually only occur after the aircraft has passed over the bow of our patrol boat. So depending on our design requirements, this might prompt us to go back and rethink our radar specification. We might look at different configurations for the targeted beam, different transmitter or receiver properties, if we need a better performing result from this probability of detection. So next up, we'll take a look at our intercept aircraft, and we'll have a look at how that's defined for its rendezvous with this target aircraft. So down here in my timeline, I can see the availability interval for my intercept aircraft 1. So what I can do is I can scrub in the timeline to kind of find the start of that point, or I can always just right-click on an element or a block in my timeline and say set animation time to interval start. And then what I can do from here is I can go ahead and show my intercept aircraft, and I can right-click zoom to. And once that map loads in, we'll see our intercept aircraft there taking off from our airstrip. I'll go ahead and pop this into real-time playback and give that a play. So we'll see that aircraft taking off there. Note that every time that I move the camera in the 3D graphics view, it's just going to pause until I let it play again. So we can see our intercept aircraft taking off there, and this is going to make its way over to our target aircraft and perform its rendezvous or its intercept. Let's go ahead and open up the properties for this intercept aircraft and take a look at exactly how that's being defined. So looking at the properties for our interceptor here, we've got our aircraft set up using the basic fighter performance model within STK. And more broadly speaking, the window that you can see here is the STK Aviator propagation tool. So Aviator really is going to allow for complex aircraft maneuvers, physics accurate models, and aircraft that at the end of the day are going to mimic their real life counterparts, both in terms of their maneuver capabilities, but also things such as fuel consumption throughout maneuvers, incorporating aerodynamic performance data, and different flight performance models for different stages of the mission. So in this case, we're using the basic fighter performance model, but I can select this button here and pick any of the other models. What I'm going to do is I'm going to pick a basic fighter copy, just a duplicate of the inbuilt model so that we can have a look at what goes into one of those definitions. So for this aircraft here, we've got 3 elements to our phase 1 of the aircraft's flight. So we've got our takeoff from our runway. We've got 2 basic maneuvers that follow that. As for the performance model of the aircraft, this is going to be defined across a number of performance models. So we've got acceleration, climb, cruise, descent, landing, takeoff, and terrain following. And because we're working off the basic fighter model within STK, it's going to have a bunch of pre-filled data for things such as our basic constraints for the aircraft, our aerodynamics, which in this case is set to the simple strategy. But what I can do here in the simple strategy, say for example, I've got more detailed information available to me, is I can choose something like the basic fixed wing strategy. And this is going to allow me to define more detail to my aircraft performance model for both the forward flight mode and the takeoff and landing mode. That's going to include things such as the maximum and the minimum angle of attack, my coefficient of lift and drag, and any other reference information I might have. Now, I can, of course, take this another step further. Like a lot of things within Ansys STK, I can actually integrate external kind of dedicated solvers and bring their results across to STK for even more detailed information. So rather than the basic fixed wing strategy, I could employ an external file, and this is actually going to allow me to bring across 6 degrees of freedom CFD aerodynamic data from, say, Ansys Fluid. Again, these are the kind of steps that as you progress through the engineering design process, you're able to integrate more and more information into your design reference mission as you go. And whilst you don't need the information to get started and to start getting meaningful results out of your simulation, the ability to add that level of fidelity down the line definitely aids in ensuring your model is going to best represent the real world system. So again, I've got those options there for aerodynamics. For now, I'll leave that as the basic fixed wing strategy. And I've also got a similar option for the propulsion of the craft. So in this case, it's just the simple method, but I can define a number of options here, once again, including an external reference file. All in all, this is going to combine to create a model of my aircraft that is indicative of my real world system, but also one where I can very quickly change from one aircraft to another. So if I want to explore various use cases, various operational cases, then this is as simple as changing out my performance model for a different aircraft, and then all of the downstream results, my intercept maneuvers, my communication elements, are all going to be computed dynamically for me as soon as I make that change. So lastly, I want to take a look at the communications aspect of this design reference mission. So throughout its flight, our intercept aircraft is tasked with not only intercepting the target aircraft, but maintaining a dependable communication link to a ground facility. Now, in this case, if I jump to our 2D graphics window, zoom in a little bit and show the headquarters facility, we'll see that our headquarters is located on the east coast of Australia. Now, to facilitate that communications link, we're using a low Earth orbit satellite constellation. So just zooming out a little bit to give us some perspective and selecting my various satellite objects and showing those in the graphics window. We can see there that we've got a kind of Walker constellation of satellites. So in this case, we've got 2 satellites per plane. There's 6 planes, and they're all equally spaced at an inclination of 45 degrees. And I've just created that constellation within STK using what's called the Walker tool. Now, each of these satellites is equipped with a hypothetical transmitter and receiver. Now, for this DRM, I haven't gone ahead and modeled those in detail, but what I could do is I could create a linked transmitter and receiver for each satellite. And by linking those objects, it means that if I make a change to any one of them, it's going to update the entire constellation. And that just ensures that if I'm working with particularly large constellations with complicated setup aspects, there's no necessary ballooning of user setup time if I'm working with a bigger constellation or if I need to change something as my project progresses. But for now, we're just working off line of sight. So effectively, this LEO constellation is going to act as a relay point for our intercept aircraft, which is able to, if I go ahead and zoom into that aircraft again, which is able to communicate to that constellation via a phased array antenna mounted on top of our aircraft. Now, this antenna, it is, given the constellation that we have, going to have more than one point of access at any given time. And we've used STK's chain object here to compute what we call an optimal strand. So an optimal strand is going to, in this case, be the route from the start object in the communication chain, in this case the intercept aircraft, to the end object in the communication chain, in this case the headquarters on the East Coast, via the path that requires the least distance to transmit that signal. Now, if I open up our chain object just to show you what I'm talking about, I've called this interceptor to Canberra. We'll see here that we've got our start object, which is our intercept aircraft antenna, and our end object, which is our headquarters. And we've got a number of defined connections. So we can go from the interceptor to the constellation, we can go from the constellation to the headquarters, and crucially, we can relay the signal within the constellation itself. And we can do this up to a maximum of 3 times. This is going to allow the signal to bounce between satellites if line of sight isn't available directly from the first satellite back down to the ground facility. As for the optimal strand, we're computing that based on distance, but we can also do that based on processing delay or a user-defined scalar within STK. Now, what this all amounts to, if I go ahead and zoom out, is we'll see this blue optimal strand. Now, in this case, how this is working is any pink strands in my 3D graphics window are a complete chain of access from my interceptor to my headquarters, whilst any blue strands is my optimal access strand. So right now, at this point in time, we can kind of see that our intercept aircraft is able to connect to LEOSat 23. LEOSat 23 is able to bounce its signal to LEOSat 42 and then down to the headquarters, but LEOSat 23 is also able to project its signal directly to the headquarters. And we can have a look in our timeline window here. So underneath the availability interval for our intercept aircraft, we can start to see the various access intervals available in our chain. And I can grab that in a report format too. So if I right-click on my intercept aircraft, intercept to Canberra chain object, and again come to the report and graph monitor, and then generate a complete chain access report, we can see the various intervals throughout our mission where we have that access. Now, of course, I can go ahead and generate those results as a report as well. So in my report and graph manager, I might want my individual strand access report. I can hit generate, and I'm going to get information about each access interval. So from the aircraft to the satellite 21 down to the headquarters, as well as information such as when that access starts, how often that particular access chain occurs, and some summary information here as far as the min, max, mean, and total duration of access for that particular link. I hope this video has provided a helpful look at Ansys STK and how that's been employed for this first design reference mission in our new digital mission engineering series here at LEAP. Keep your eyes peeled for future entries into this series. We'll also have some guest blogs from in-industry use cases going live on our website at our new DME blog. And if you've got any questions, by all means, reach out. We'd love to see how this technology can be applied to your industry or your application. Thank you very much.